All right. Yay. Welcome back to the session. Am I audible? I want to hear some voice. Am I audible? Would you mind?
Yes, yes.
Yeah. Okay. Thank you. Thank you for answering that. Really appreciate it. Right. So, yeah, without further ado, let's get started to the next session of the presentation. We still have 3 groups left. We have group 3, group 6, and group 7 for the presentations. For group 3, are you ready to go up to the stage?
Yeah.
Yep, perfect. Then you can start sharing your screen. And while we are waiting for it, I just want to remind you to keep your presentation succinct, and you need to also pay attention to the timer that the IVC Astronomy account is sharing with you. Okay, I see that you are ready for the presentation. So group 3, the screen is yours.
Right. Good afternoon, everyone. We are group 3 and we are going to present our project, which is stellar evolution modeling. Next. So this is our tutor. The slides are prepared by my friends and we are the presenter. Next, please. So we will start our presentation with the methods, then the result and discussion, and finally the conclusion. Next. Before I start with the method, I would like to start with a very brief introduction. A stellar evolutionary model is a mathematical model that can be used to compute the evolutionary phases of a star from its formation until it becomes a random. Extensive computer calculations are then run to determine the changing state of the star over time, using a table of data that can be used to determine the evolutionary track of the star across the Hertzsprung-Russell diagram. Next. In this project, we use MESA-WEB to model a one solar mass star from pre-main sequence until white dwarf. Then from the data, analysis and plotting was done using Python codes, mainly evo.py and structure.py. Next, please. By default, MESA stores its data in the logs directory. The history of the run is saved in the file called history.data. The file provides general information about the entire stellar model as a function of time. By reading the file with Python, we can obtain the model number with star age of 4.67 billion years. That is for question 1 in our project. We then use the model number and search in profiles.index to find the corresponding profile. The profiles contain information about the internal structure of the stellar model at a single time step. And each profile includes both a set of global properties of a star, such as its age, a large set of properties for each point in the model of the star. Then we run structure.py with the selected profile. Next, please. Okay, coding time. Actually, our code is quite simple. We follow the codes given by Dr. Lisa. And then, for example, this is a code that is used to filter out the data at a given star age. Next, I will pass the floor to my friends.
Good afternoon, everyone. Next slide, please. So here I am with the results of our stellar evolution model, which is one solar mass evolution from zero age main sequence to current age of our sun, that is 4.7 billion years. Next slide, please. So yeah, in this slide, our team has depicted the amazing models that is shown in the left-hand side, which is the relation between central temperature, the mass, age of the star. So we'll get back to that in a moment. It shows the important two aspects of a star when it's that's happening in the first half lifetime of its existence. The first one is the proton-proton chain. That is the reason for converting the hydrogen into helium through fusion. So as you can see in the core, the hydrogen is constantly turning into helium. So as helium is higher in mass than hydrogen, the density of the core of a star is actually increasing. So as the temperature of the core of a star increases, it creates a hydrogen shell inside the star, and the constant increase in the internal density of a star supports the hydrogen shell around it. So in the first graph, we've shown the central density with the central temperature, which is pretty linear relation. And in the bottom of the graph, we have the mass and age relation. So as constantly the mass is getting converted into energy, the lot of energy is released in the form of radiation, gamma radiation, neutrinos or positrons, for example. And we have this the element transition graph, which is the hydrogen is getting converted to helium. So the amount of hydrogen percent in that star is decreasing as star is constantly increasing, and then the nitrogen is pretty constant because it's not involved in this cycle. So next slide, please. So yeah, the second important thing I wanted to talk about is the structural changes of a star, which we have here in mass and radius, luminosity and radius, the temperature and the radius. The fundamental principle of our radiation process is that the Stefan Boltzmann's law. So the luminosity is directly proportional to the radius. That's what we can see here in the top right graph. The luminosity is decreasing as the radius is decreasing, and we have the temperature and radius graph. The radius is inversely proportional to temperature, so the radius is decreasing and the temperature is increasing, or vice versa. And we have this the element transition table, the graph as we have shown in the previous slide. So I am passing my slide to my other colleague.
Okay, for the result 2, it is 1M evolution from current age of the sun, white dwarf. Yeah, as mentioned before, the end of the main sequence phase of evolution occurs when hydrogen burning ceases in the core of the star. The core begins to contract while a thick hydrogen burning shell continues to consume available fuel. The rising temperature in the shell due to contraction, the shell actually produces more energy than the core did in the main sequence, causing the luminosity to increase, the envelope to expand slightly, and the effective temperature to decrease. The shell continues to consume the hydrogen. The helium core steadily increases in mass and becomes nearly isothermal. Then the Schoenberg-Chandrasekhar limit is reached. The core begins to contract rapidly, causing the evolution to proceed much faster. Next. Please. As the core contracts, the non-zero temperature gradient is soon re-established because of the release of gravitational potential energy. At the same time, the temperature and density of the hydrogen burning shell increase, and although the shell begins to narrow significantly, the rate at which energy is generated in the shell increases rapidly. Again, the stellar envelope expands, absorbing some of the energy produced by the shell before the energy reaches the surface. Then the star begins to climb the RGB in the HR diagram. Its effective zone depends until the base reaches down to region where the chemical composition has been modified by nuclear process. The nuclear processing has increased. The surface convection zone encounters this chemically modified region. The processed material becomes mixed with material above it. This transport of material from deep interior to the surface is referred to as the first dredge up phase. At the tip of RGB, the central temperature and density have finally become high enough that quantum mechanical tunneling becomes effective through the Coulomb barrier, allowing the triple alpha process to begin, resulting in C and further processed into oxygen as well. With the onset of a new and strongly temperature-dependent source of the energy, the core expands. Although the hydrogen burning shells remain the dominant source of the star's luminosity, the expansion of the core pushes the hydrogen burning shell outward, cooling it and causing the rate of energy output of the shell to somewhat decrease. This results in the abrupt decrease in the luminosity of the star, and at the same time the envelope contracts and the effective temperature begin to increase again. Next, please. I'll pass this to Sabrina.
Okay, the next part is the result when we calculate one solar mass from zero-age main sequence to white dwarf. We can say that this is the bigger picture from the two parts before. Next. We can summarize what happened at the core of the star from the history plot here on the right side. It is easier to see the stellar evolution from the nuclear reaction standpoint. We can see that there is a change in the main chemical properties in the core. At first, we have the PP chain reaction, as mentioned before, that indicated by the increasing composition of the helium in the core. Eventually, this helium becomes the more dominant one, but the PP chain still continues until the complete depletion of the hydrogen in the core. This change, of course, comes with the readjustment with the structure of the stellar interior. This readjustment may involve expansion or contraction of the core or envelope and the development of extended convective zones. When the core of the star consists only helium, like we see on the graph, the energy radiates from the nuclear reaction in the shell at this point, burning hydrogen, causing the expansion of the envelope. The main sequence ends when the helium core collapses after going through the Schoenberg-Chandrasekhar limit. And as the helium core continues to collapse, the core becomes strongly electron degenerate. When the temperature and density become high enough to initiate triple alpha process, the initial energy release is almost explosive, that the ignition of helium burning occurs, initially in the shell around the center of the star, but the entire core becomes quickly involved, and then the temperature inversion is lifted. This tremendous energy only lasted for a few seconds, and most of the energy never reached the surface of the star. Instead, it is absorbed by the overlying layers of the envelope, possibly causing some mass loss from the surface of the star. In this case, the carbon-oxygen core, as the result of the triple alpha process in the core, will never become large and hot enough to continue nuclear burning. And long story short, at some point during the insane final phase of the mass loss, the remainder of the star's envelope is expelled, revealing a hot central object that will become a white dwarf star, which essentially is the old red giant's degenerate carbon-oxygen core, surrounded by a thin layer of hydrogen and helium. Next. Next, please. This is the simplified illustration for evolution of one solar mass star from the protostar to main sequence star, and then to red giants that continues to expand its envelope, that eventually that envelope is expelled because of the mass loss and revealed a degenerate core that is red giant. And that's it for me. I will pass it to Adam.
Okay, now for the conclusion. Next. First conclusion, there are relationships between chemical composition in star and stellar evolution. Second, change of temperature and luminosity can describe evolution phase of a star. And third, there are several evolution phases before a star can be a white dwarf. Next, please. This is our reference. Next. Thank you for your attention. Any question?
Okay, thank you. Any questions or comments, maybe suggestions? No?
Yeah, okay. I'm going to give some comments a bit. Can I?
Yes, please, Dr. Lisa.
Yeah, okay. So I have seen the presentation and I see that you guys, what we call it, you use the MESA web instead of the technique, the evolution using the MESA code. Okay, it's okay. It's just that my comment about when you want to present the result, I know that I give the code is kind of like a very simple one, a crude one. And you have explained about the nitrogen is a bit low and something like that. Yes, it's not really what we call it uniform or in equilibrium. In that sense, it's just that the nitrogen is very small fraction, and usually when you want to plot the elements like carbon, nitrogen, and also oxygen, for example, for stars, we plot different plot from hydrogen, helium, what they call it, fraction due to the difference in the mass fraction. So if you plot, if you create another plot to see the nitrogen, what we call evolution or structure profile, you will see there is what they call it some what they call increase and decreasing of the element itself. Yeah? So that is, I didn't explain in the lecture last time, but I think that you can try to play around with the code and also the structure and profile Python code, and then try to plot other elements, for example, the abundance, the energy, and so on, so that you can understand the one that you presented, so be consistent with your slide. That is my comment. Thank you.
Thank you, Dr. Lisa, for the comment. Any comment from the group to that? Maybe do you get what Dr. Lisa had been explaining to you? Yeah?
Yeah, thank you, Dr. Lisa. We will definitely try to improve, because from the MESA web, from the MESA web data, there is more data for us to play around.
Yeah, that's why I mean that when you plot, I think that you just take a very, what do you call it, example from what I've given. So next time, I think the rest of the class, you can try to play around with all the elements, right? Great.
Right. Thank you for the comment, Dr. Lisa. Any more comments or questions? Maybe a short one. We still have about 2.5 minutes before this turn ends. Oh, Ali only gave his claps. Right. So maybe I do. Oh, is there anyone who wants to ask questions? Hassan, would you like to ask any question? Oh, okay. No, I don't think he would. Right. Anyway, maybe just a short comment from the group. I have one short question. So what have you learned after doing this experiment? Do you get like a new knowledge, for example, in this field? Or do you like, oh, I've known everything in this field, so yeah, I got nothing, for example. Anything new that you have learned after, conducting this experiment?
Yeah, can I talk?
Yep, sure.
Now I'm in my final year of undergraduation, and I'm actually doing my project on stellar physics and the stellar spectroscopy. So I've been doing this absorption lines and emission lines using the CCD, and also this modeling and simulation really improved that a lot to improve the knowledge I got from my college project. So it helped me a lot to do my college projects as well.
Okay, cool. Thank you. Azimukhilan, was it? Yeah, I thought so. Okay. Anyone else in the group who would like to give like a short comment, maybe?
I would like to add something. As a physics student, we don't have a stellar physics class, so it's like a new experience to me. Like I can't say that I know everything about stellar physics, but I learned a bit about one mass stellar evolution. So yeah, I think it's really important to me. Like it leaves something in my head, in my heart. It's interesting, I guess.
Awesome. Thank you, Aulia, for the comments. And yeah, that's it. I think that Aulia's remark will end this session. I mean, group, what was it? Sorry, I forgot. Is it group 3? Yeah, I think. Okay, thank you. So let's give a big applause for group 3 for their presentation. You can stop sharing your screen now. And okay, let's move on to the next group. So let me check. Right, so 2 last groups left. So the next one would be the N-body simulation by using Amuse. So this group just changed their topic like last minute because they thought that the initial topic was too difficult to do. So they proposed to do this topic instead. So are you ready to present this topic, group 6? Perfect. And then if you're ready, then you can start sharing your screen, and we'll be waiting for you to get ready. And before that, okay. Right, so no more comments from me. Okay, so without further ado, let's get started. The screen is yours.
Okay, thank you. Hello, everyone. Good afternoon. So we are from Group 6, and in this session, we will talk about N-body simulation and stellar evolution with Amuse. So our group members are Dante, Shania, Shahna, Salam, Atika, Sofia, and Hidayah. In this session, we will going to explain about Amuse and a brief explanation what is Amuse and how we do it, and the examples in N-body simulation for star cluster and stellar evolution.
So Amuse stands for Astrophysical Multipurpose Software Environment, and this is a framework for astrophysical simulations. Its goal is to provide a homogeneous environment to set up, run, and analyze simulation codes, enable new code couplings and interactions between components, and facilitate multi-physics and multi-scale simulations. The few examples of what it does is creating N-body simulation for star cluster, stellar evolution.
Okay, next. I'm sorry, I cannot turn on the video due to the unstable connection. So N-body simulation. Next. So in N-body simulation, there are a few steps that we have to do before. So the first step is we determine the initial condition for the N-body, where in this analysis, we perform on a 100 star cluster in a 1PC virial radius king model. And the stellar masses we are taken is randomly from a salpeter distribution. And in the simulation, we ignore the stellar evolution. Next. Now, I'm going to explain a little about the salpeter function or the salpeter IMF. Maybe, yeah. So this is a form of the IMF where we have some coefficient called alpha, where the alpha in his work is favored an exponent of alpha equals to 2.35. And it shows that the number of stars in each mass range decreases rapidly with increasing mass. The salpeter initial mass function is, as you can see at the equations on the screen, where m with the sphere below is the solar mass and the epsilon 0 is a constant relating to the local stellar density. Next. Now, here are the codes that we use to install the packages and import the libraries that we are going to use. Next. Yeah, we import the NumPy, the pyplot, the units constant, the n-body system, and etc. Next. Now we are ready to set up a simulation by specifying our stellar mass distribution and plot by the salpeter function. So as we have determined before, the number of the stars is 100, and the alpha IMF is equals to minus 2.35 to satisfy the salpeter function before. And we determine the m stars randomly. And after that, we plot the x and y, where x is the mass of the stars and y is represent the cumulative probability. So we will see the plot next. Now this is the IMF plot. So as you can see on the plot, there are two curves. The first curve is the dotted curve, and the other one is the orange one. So what is the graph shows? So it shows that the number of stars in mass range decrease if the mass is increased. Why is that? It is because the massive stars have a shorter lifetime due to the nuclear reaction. So we will observe more low mass star than the massive one. And the dotted curve does not overplot with the solid curve. It is because the curve is some mathematical equation, and it's actually an exponential equation that we get from the salpeter function. And then the orange plot, it is the star that we generate using some random number. So that's why the result will not exactly fit the blue line. Next.
Okay, so I will continue about the n-body simulation. I'm sorry before if my voice isn't really clear because I have a sore throat. So this code is the notebook tutorial on generic units in Amuse. On the upper code, we start to convert the units. And on the code below that, we change the gravitational constant to have the numerical value 1. This is to simplify the n-body system equation. Next, please. After converting the units, then we can check it by plotting the stars here as a particle to a two-dimensional scatter plot using the code. Next. So this is the scatter plot. The x and y axis is the star's position or distribution on the cluster. Its star's velocity are also shown as different colors on each dot. The higher the velocity, the brighter the color. As we can see, the closer a star to the center, the higher its velocity due to gravitational fields. It is also depends on its mass. Next. Then we use another code to evolve the cluster in time by using one of Amuse n-body integrators. With this code, we can calculate the dynamical evolution of a small cluster of stars, including or realistic mass function. Next. Here is the result of the code before. The output is the cluster's age, mass, and the virial radius of the cluster. Next, please. Okay, so this is the evolution of Lagrangian radius and virial radius that is already plotted. Orange line is the virial radius and blue line is the Lagrangian radius. So Lagrangian radius is the radius of Lagrangian point. Lagrangian point is the point where the gravity potential is zero in n-body system. So the Lagrangian radius is the distance of the Lagrangian point to the center of mass. Lagrangian radius keep changing because the stars in the cluster is not moving in perfect circle. It depends on the star's movement of that time. As for the virial radius, it's the radius which the virial theorem applies on a gravitationally bound astrophysical system. Virial theorem relates the total kinetic energy of a self-gravitating body due to the motion of its constituent parts. Both of these graphic depends on the movement of the star, so the graph shape is similar. That's all for the n-body simulation. Next, we will discuss about stellar evolution using AMUSE with another group member.
Okay. Hello, can you hear me? Okay, now we move on to stellar evolution. So in this section, we will learn about how to generate initial condition, which is the mass function, and how to write a parameterized stellar evolution code, channels and data transfer, and plot the results. Next. Okay, the first step is, of course, to install all the packages and importing the libraries needed. Since we're in AMUSE, we can just get all the stuff from AMUSE. Yeah, already built in AMUSE. Okay, next. All right, and then we have to set up the initial condition to evolve one solar mass star for normal zero-age main sequence star. So P particle means we make the particle with the mass, one solar mass, and then S equals to SSE, that is the stellar evolution code incorporated in AMUSE. We declare the code. There are many stellar evolution code in AMUSE. There are MESA, EV-Twin, SEBA, TOI, but since we want to learn about the parameterized one, we use the SSE. Okay, and then we have to add the particle and evolve the model. And after setting the initial condition, we get the printing about the initial age is 1 megayear, and then the initial luminosity and initial temperature and the time steps. Next. Okay, setting the stellar population. The number of stars we are using is 1024, and the minimum mass of the star is 0.1 solar mass, and the maximum is 100 solar mass. And we are using two different mass distribution, which is the Karupa and Salpeter. And then we'll print the min mass for Karupa and Salpeter. Karupa and Salpeter is the commonly used mass function. Okay, and then we plot the mass function. Next. So after plotting, we get the min mass equals to 0.63 for Karupa, and Salpeter is 0.40 solar mass. So there's a bit of difference. Salpeter is the pioneer in the value of IMF, and Karupa is the bit new one, developed in 2001. So there's a difference. Later I'll talk about it. Okay, I pass to Sophia.
Okay, I will continue from here. For now, that the mass function are determined, we can solve the star in time for this type. For this, we start the stellar evolution code that is parameterized and evolve the star in time. We use mean mass distribution from Karupa and Salpeter in previous slides, and then
we can get the different result for the evolution. We use because we use mean mass distribution for Karupa and Sapiter. They have different structure, and that therefore we use two different channel and to differentiate between these two. Next. Okay, after the evolution, code is declared. We evolve it in time, and then we calculate the mean mass as a function of time. For this one, this is the code that we need. So next. Okay, this is the answer. The evolution that we get, the time that we get from the calculation. The program would print this while evolving the star before eventually printing the new mean mass of the star. So for the new, after the evolution, the mean mass for Karupa is 0.37. For Sapiter is around 0.27 solar mass. So next. Okay, for this one, we plot the graph for the relative mean mass versus year of evolution. As we can see in this graph, in general, we can say that the mean mass decrease with after the evolution due to different burning stages, different evolution of the star depending on the inertial mass of the star. Different mass undergo different evolutionary track. Low mass will go through burning stages at low rate, while the massive star will go through rapid burning stages. So we can see that for the lowest mean mass, we can get longest evolution time. Next. Next, please. Okay, for this one, we plot the HR diagram for 1024 stars with solar metallicity and inertial mass between 0.1 to 100 solar mass, and we evolve it to an age of 7,493 mega years. The star we evolve using a rapid single star evolution SSE. And in this, we use different mean mass distribution. For red dotted here, Sapiter. For the blue one is Karupa. Since we can compare the graph that we get from SSE code, and then we compare with the HR diagram that will show how this our distribution star fall into this group. For our star, usually for our star, they fall into the giant branch, and then the main sequence star, and also for the main sequence star, and then for the below here is the white dwarf evolution that I think this is the final product of the evolution of the star itself. I think that's it for the discussion, and then I pass back to Dante.
I'm sorry, but
okay, maybe that's all for our group. And yes, and thank you for your attention. Any question? Yes, Ali.
Okay, maybe I can ask some question.
First, I want to know what is the use case of using Muse with respect to observation, maybe? Can you give us some example?
I'm sorry, Ali, could you repeat the question?
Oh yeah, the question is
There's some
what
like
is the use
buzzing.
case of the thing you're doing, the project, with respect maybe with observation, what can we do with the information or whatever you do here, with maybe I have some data from observation.
Okay. With the Muse, in my opinion, with a Muse, we can simulate and maybe we can predict the amount of star clusters. Like example, if we observe star clusters in the reality and we want to know what would it be like in the future, and we can simulate it with a Muse. With the N-body system, we can simulate maybe the size of the star cluster and maybe the size, the radius, virial radius, and Lagrangian radius. But if we use the stellar evolution, we can predict each star evolution in the star cluster. So if we use both of them, we can predict and get more information, and we can simulate in the star cluster in the future, like that. Is it answering your question?
Oh, okay, thank you. And maybe last comment from me. You can see from this graph, can you see something wrong maybe about this graph? Anyone can?
Which one?
The graph you're showing right now.
In this slide? Or in this slide? Yeah.
Oh,
okay.
That one.
Wait.
The last one you showed to us.
The
maybe this
one.
You can show me this graph, and can you find something wrong with the graph maybe? Because I cannot see the label. I don't know what is the x-axis from this one, or the title, or maybe the legend, even though you put some description. So maybe that's my comment for you. For y'all, you haven't put any label to most of the graph, but some of the graph has label. That's interesting. Maybe that's all I can.
Okay, thank you, Ali, for the comment.
Right, thank you. We still have about 1 minute and a half left. Is there anyone who would like to give more questions, more things to discuss? Maybe keep it succinct if you still have any questions or comments. Oh, Pak Iqbal does. Yes, please, Dr. Iqbal.
Yeah, thank you. Solis, can I see a plot, the first plot about IMF, initial mass function, that you calculate in your code? Yeah. What is the x-axis?
Okay, the x-axis is the stellar mass, and the y-axis is the distribution.
So this means that the high mass is what's it? Distribution. It's more abundant than lower mass.
No. This plot is a cumulative distribution. So the steeper the line will, it means that the probability is higher. Yeah, the number is higher.
I don't understand. So the cumulative mass. So if the higher mass is more many higher mass, so it will be steeper, right? So why is it different with the other initial mass functions in your code? They are from Krupa and Salpeter. Not 2 histogram. Yes, this one. This one is higher mass. It's fewer than the low mass. Not the histogram. Okay. Yes, this one. Is there any difference with this plot or explanation with the first one? Yeah, I know the first one is a cumulative, but it's cumulative, so the lower mass should be steeper, and then the higher mass should be more less steep. Is that so?
To be honest, I don't really understand this graph.
Yes.
Yeah.
Okay, this is initial mass is how we want to know that if the cluster were formed from the cloud after the collapse, so how many stars were formed, and then which star has a mass. So in the Salpeter and Krupa, so less mass, the star with lower mass is more abundant than the higher mass. So the physical means that. So we are so there are not so many star with mass more than 10 or 20. There are, but very few. Maybe Dr. Riza can explain what many stars with a very high mass. Okay, that's all from me. Thank you.
Okay. Okay. Thank you, Dr.
Thank you, Dr. Iqbal, and thank you, Group 6, for presenting your presentation very briefly. Although you just told us that you don't really understand this, but that's fine. That's the process of learning. Yeah. Okay, so let's give a round of applause for Group 6. Thank you, and you can stop sharing your screen now. We are moving on to the last group here with Group 7. Group 7, are you ready? Oh, Dr. Lucky actually has this question, but I'm so sorry. I think the discussion can be followed on Slack maybe. Yeah, I'm really sorry about that. Yeah, okay, thank you. Anyway, what about Group 7? Are you ready for the presentation? I know that you're the only group who has a member living like on the other part of the globe. There's someone in Group 7 who are currently living in Colombia. It's like 12 hours from Indonesia, so it's about 3 a.m. in the morning now. So are you ready to present your project?
Yes.
Okay, then you can start sharing your screen so that the audience can see what you're going to present. Oopsie, that's the slide. You? Okay. Yep. Yeah, all right. Thank you. So since you're ready, now the screen is yours.
Okay, thank you for the time. Let me start. Good afternoon, everyone. As you can see on the screen, we will present about galaxy formation using dusty stage, which was discussed by Group 7. So
Okay, our team member were Agni Saloma, Lukman, Juang, Ashraf, and Steve Gerardo. And our tutor team is Sulis. Okay, this presentation is structured as follows. The first, introduction about galaxy formation. And then the second one, the methods or process in finding the solution of exercise. The third is conclusion, and the last one, timeline, will in doing the assignment. Okay, introduction about galaxy formation. How a galaxy form. As astronomers use the fundamental laws of physics to give the basic story of galaxy formation. Gravity pulls matter together to form filaments. Galaxies form out of immense clouds of gas that collapse and rotate. As they evolve, stars form within clouds of matter collapse. Galaxy contracts and rotates faster. Collision on the gas to produce a D-shaped spiral galaxy. Looking deep into space, we see galaxies at earlier stages in their lives and learn more about their evolution. They are more numerous, display unusual shapes, and have episodes of energetic outbursts. Okay, next. Now, so how we can modeling the galaxies? We know Dusty Sage. Dusty Sage is a semi-analytic model for galaxy formation that includes a detailed prescription for dust evolution. This model is a modification of semi-analytic galaxy evolution given by Mrs. Priani. Dusty Sage runs on any n-body simulation whose trees are organized in a supported format and contain a minimum of basic Hello properties. Next.
Okay. Hello, everyone. Can you hear me?
Yes.
Yes. Okay. Right. Okay. Hello. Hi. I am Ashraf, and now I am going to share with you the initial method that we use in our assignment. So for our assignment, or our task, the initial method used to solve the problem was to generate the galaxy models. So totally, there are 5 questions available for us to solve, but a few procedures need to be completed before we were able to generate the galaxy models. So firstly, we installed the packages, which is the Dusty Sage. It is available on GitHub and can be installed directly onto our computers. Okay, next. Okay. And then secondly, we generate the galaxy models specifically with 8 different values of redshift. Okay, so I listed also here some values of the redshift. So we use the default settings or initial conditions for all the initial models that were required to generate the galaxy models. This includes the dust model, the star formation model, the merger model, and this instability model. So these are the models that were required to generate a final output of the galaxy models. Okay, so this was done by editing a parameter file named a minimillennium.par file, followed by running the packages using the Sage command. This then consequently creates a snapshot output file for every value of the redshift, where this is important, where we can quickly restore the calculations at a specific time if there are any mistakes, accidental deletions or data corruptions during the computation. So you can see there are about 64 snapshots available in the figures. Each set representing one value of a redshift. Okay, so each of these galaxy output models generated contains a lot of information or parameters, which include, for example, baryon fraction, black hole mass and its growth rate, and also information about the gas. Okay, so all this information can be used subsequently in the exercises. Okay, next. Okay, so finally, to be able to use the properties of the models of the galaxy models that have been generated, we used Jupyter Notebook, where the exercises are available in the iPython notebook, or simply known as IPYNB format. Okay, so next, my group member Lukman will share with you the computation that has been done for each question and the results obtained.
Hi, hello everyone. I'm Lukman. So I'll be explaining about the exercises portion that was given for the assignment. So in the assignment given, we have 4 exercises and 1 bonus question. And so we'll take a look at these exercises now. So yeah, for the first exercise, we're required to find the percentage of galaxies with mass greater than 10 to the 10 solar mass over the Hubble constant. And this is to be done in for redshift 0, 1, 2, and 3. And so before I go further, let me quickly introduce what the variables here mean, to understand a bit about how SAGE works. So basically, when we perform our calculation of the model, so to access our galactic data, we use this what's called the G history variable here. And so we use if you see here, we use the index 0 here to get the data for redshift 0, so Z equals 0. And so we can do this for the different redshifts. So we can take G history 1, 2, and 3 for the different redshifts. And so so in this after we do that, we basically can get any characteristics that we want. So in this case, for example, we take the stellar mass, and so we saved it as a variable, and we can see it's a list of mass of all the galaxies in that particular redshift. So yeah, so then to do the first exercise, basically we just filter out what we want and divide it by the total number of galaxies, and then turn that into percentages. So in the plot, next slide please. Yeah, so in the plot here, we can see that this is the percentage of galaxies more massive than 10 to the 10 solar mass over the Hubble constant. And then basically, yeah, in the plot, basically, we see that the percentage of galaxies basically decreases linearly as redshift increases. Next slide. For the second exercise, we have to find the percentage of spiral galaxies at each redshift. So we do pretty much the same thing as before, but we have to calculate the bulge to total mass ratio, and so we use that as our filter. And then next slide. Yeah, so from this plot, we note that it generally increases as the redshift increase. So starting from redshift 1 up to redshift 3, it basically increases, but except for the first, except for redshift 0 to redshift 1, where it was actually a huge drop. Okay, so now let's go to exercise 3. So for exercise 3, we are asked to plot the stellar mass function, which is the number of density, as a function of stellar mass. So this is done for star-forming galaxies and also quiescent galaxies along with the total stellar mass function and also what has been observed. What has been observed outside our simulation. Yeah. So from the next slide. So another next slide. I will just skip this part for now. So from the plot, we can see that the stellar mass function for star-forming galaxies is higher than the quiescent galaxies at lower mass. Log 10 star mass less than the 11 solar mass. Right. Yeah. Okay. So next, for the fourth exercise, we have to plot the median dust to gas ratio across redshift 0 to redshift 7. So with the plot, we can see the evolution of the dust to gas ratio. Next slide. Sorry. This slide. Okay. So which we can see the plot that it basically decreases slightly from 0 to 3, but it increases rapidly afterwards. So next slide. So lastly, for the bonus exercise, we are asked to run Dusty Sage again on the mini millennium simulation, but this time with the AGN feedback and supernova turned off. So when we plot the stellar mass function, right here we can see that there's an increase in the number density of low mass and the high mass galaxies. And so this means that the AGN feedback and supernovas, they basically suppress the star formation activities. So if we turn that off in the simulation, you can see the increase in star formation. Yeah, so yeah, that's it for the exercises portion.
Okay, guys, here is the conclusion of our work. The use of semi-analytical model to galaxy formation allow us to develop calculation easier. The percentage of galaxies with mass higher 10 to 10 solar mass per hour is lower with the value of redshift. The percentage of spiral galaxies generally increase with increasing redshift, except at z equal to 0, where it's at its highest. The stellar mass function for star-forming galaxies is higher than for quiescent galaxies at lower mass, but almost converge together at log 10 m star more than or equal to 11. The DTG ratio decreased with the redshift, AGN feedback, and supernova suppress star formation activities. So removing this from simulation would increase the number density of low mass and high mass galaxies.
Okay, finally, this was the timeline in doing the assignment. The first step was recognize the issues. The second was investigate about the problem and little about the Sage, especially on Dusty Sage. The third step was install Sage. The fourth step was understand and resolve each exercise using Python codes. Next, please. And the fifth step was discuss the astrophysics around each outcomes, and the sixth step was conclude about based on the results. Okay, next. And how Solis mentioned it before, we was a big problem because we live in different countries, but we don't worry about the distance because we do the discussion section using Zoom, or even we use Slack wall. The next, please. And this is the reference. Next, please. Yes, and we are glad to be part of this virtual summer school and for the opportunity to share your knowledge with us. Thank you for all. And if do you have any questions or suggestions?
Okay, maybe I can ask something. Can you show the conclusion slide again? Okay, this one. From this conclusion, do you think the result is consistent with what we know from observation?
what conclusion are you speak about, especially specifically?
Maybe you can talk about each one, each of the conclusion with what we know from observation. Is it consistent or has some paradox or inconsistency, something like that?
Yeah, so maybe I could talk a bit about this. So for at least for the first exercise where we have the we are asked to calculate the percentage of galaxies with mass higher than 10 to the 10. It seems yeah, I think it basically follows what we kind of knew. Percentage. Yeah, never mind. Yeah, so for the first exercise, with the mass, it seems to concur with what we knew about. So if we have a higher value of redshift, it does seem that the percentage of galaxies with higher mass than this value they get lower. For the second exercise, so along with this question by Dr. Loki, percentage of spiral galaxy increase. Yeah, so at least as far as I understand, redshift is basically just it's a measure of distance first and foremost. Basically, whatever that we're measuring, we're basically measuring when we observe something with a high redshift. Basically, we're observing something that comes from a really far away. So it takes a really long time for it to come to us, and so we can also generally say that something with a high redshift is older. So with that, with that in mind, so thinking about the question about the percentage of spiral galaxy, so generally it's been said that spiral galaxies were created in the early universe, and then after some time we have spiral galaxy mergers, and then when we have these spiral galaxy mergers, they will become elliptical galaxies, and so we can basically see that in our graph. Basically, as it comes towards redshift 0, where so basically as we go forward in time, there are less spiral galaxies as they have become elliptical galaxies. So yeah, so I think in that sense, it's kind of agree with what we know about that. Yeah, does that answer the question? I hope so.
Okay, thank you for the answer. And I want to add something about the redshift. It's not only a proxy for distance, but also a proxy for measuring time. So we also seeing the galaxies in the past time. And maybe the last thing I want to ask about the dusty sage. Do you need to insert the age of universe maybe to run the simulation, or is it just defaulting to the current age of our universe?
Sorry, can you repeat the question, please?
Do you need to insert the age of the universe when running the simulation, or is it just a default value of our current universe?
Okay. I don't know. I am not sure about that.
Yeah, when we ran this for this exercise, we basically ran it before. So we did not really change anything. But I'm guessing in the parameter we can change that parameter. So yeah.
Okay, thank you.
Thank you. And I suppose this will conclude the last presentation session. Thank you, Steve, for staying awake despite the time difference with the power of will. Yeah, thank you. And let's give a round of applause for group 7. All right, so that's it, everyone. We are nearing the end of the session, and it's now like 5 minutes to 4 Indonesian time. And after this, we will have some kind of award announcement. So who will be maybe the best presenter, and who will be, I don't know, maybe the most favorite participants, that kind of things. But before that, let's have a break, and then you can have maybe like some coffee, or you can just relax or stretch out, because I know that you may have been sitting for quite a long time, and it's not good for your, your muscle and your bones. So yeah, let's have like 5 minutes break, and after that we can go back here, and we will deliver the awards for you. Okay, thank you and see you.